So in the last video, we have discussed the variational method as an approximation for quantum mechanical problems. Okay, here we are applying this method for a 1D linear harmonic oscillator. One thing that you have to know is that we do not require an approximation method for the linear harmonic oscillator. The solution for that is exactly no. Okay, so whatever you're doing from the approximate uh, method, it has to give you the actual solution or something close to the actual solution. Okay, depending upon the quality of your trial wave function, you'll be getting close to the uh, true value. And if you're taking the kind of a suitable wave function, you will be able to exactly produce uh, the exact solution of linear harmonic oscillator by using this variational method. So that's the idea. And let us start with our ground state of linear harmonic oscillator. So right now I just want to find out the energy corresponding to the ground state of a linear harmonic oscillator. So first thing I need to know is the Hamiltonian of linear harmonic oscillator, and that is nothing but p square by 2m over minus h cross square by 2m. As it is a linear harmonic 1D linear harmonic oscillator, you can take only the x part of it, plus you have the potential term, that is half k square or m omega square x square. So that's a Hamiltonian, and we have to take a suitable trial wave function. So this is a difficult part. To understand psi node, you have to understand what and all are the properties of the linear harmonic oscillator at that particular state. You have to know the behavior. So most of the cases, when you have to apply the variational method, this will be provided for you. Uh, in case if it is not provided, the wave function will be of a familiar form. So in this case, for a linear harmonic oscillator, for its ground state, uh, like any other wave function, the first condition that we can take is that as the psi tends to minus infinity or plus infinity, the wave function has to go to 0. And for ground state of linear harmonic oscillator, it's a smooth wave function without any breaking. And uh, yeah, there is no node coming in between, no dip or anything. So it's a continuously decreasing sort of a function. So something like this. You know the actual form, but yeah, from the basic understanding about the state of that linear harmonic oscillator, we will be getting something like this. So this require some sort of a previous knowledge about the system to really guess the trial of wave function. Okay, so once you guessed, you can somewhat, like in this case, you can approximate it as a Gaussian kind of a profile. So the functional form that you can take is something like a normalization constant e raised to minus ax square. Okay, a generic form. I don't know the width of this wave function, so it's I just kept it on a parameter, and this is actually the adjustable parameter that I'm talking about. Adjustable parameter. Okay, so depending upon the case that we have to finally choose which value for that is kind of convenient, is most likely the corresponding to the ground state of this harmonic oscillator. So the working procedure is something like finding out the energy function, and that is obtained with this expression. If you have a trial wave function, let's say psi naught uh, h cap psi naught divided by psi naught if it is not normalized. Otherwise, the best way to do is just normalize it and continue with the above expression. So I'm just normalizing this wave function now. So psi naught will be something like integral minus infinity to infinity a square e raised to minus 2 times of that 2ax square dx. Okay, so this is actually standard integral, and you know the solution of that. Standard integral is integral minus infinity to infinity e raised to minus 2 no, e raised to minus ax square is equal to root pi by a. This is kind of a standard integral formula, so you can just apply uh, that here. Here instead of a, what we have is 2a, and there is no difference. So the normalization condition will assure that this quantity has to be 1, and what I will get is a square into root pi by 2a equal to 1, which will give you a square equal to root 2a by pi, or a equal to 2a by pi whole to the power 1 by 4. So that is your normalization constant. Now the second part is to do psi naught h cap psi naught. Psi naught h cap psi naught. Okay, so I'm splitting h cap. H cap is having two terms. One is a kinetic energy component, another one is a potential energy component. So in the first term I have constant like minus h cross square by 2m, and then there is an operator dou square by dou r square. So I have to put it at the correct place here. I'm just splitting the entire equation as two terms. Psi naught first term will be having dou square by dou x square remaining, and again psi naught will come plus. Now the potential energy term is nothing but half m omega square psi naught x square psi naught. Okay, so first we will calculate this quantity and substitute later. So one by one we will do psi naught dou square by dou x square psi naught. So psi naught for the time being I am taking a form, and later I will substitute the value. So this is going to be anyway both side a will be there, which will give you a square in the expression minus infinity to infinity. Psi naught is e raised to minus a x square dou square by dou x square e raised to minus a x square dx. Okay, so we have to integrate or differentiate this e raised to minus a x square here. So this will give you a square minus infinity to infinity e raised to minus a x square, and differentiating first uh, let me differentiate it first with d by dx. So that will give me an e raised to minus ax square again, and the differentiation of minus ax square, that is minus 2ax into dx, or this much part is same, and I'm just taking this part and differentiating it. That will become okay. So if I again differentiate this term, again a minus 2ax will come, so that will be plus 4a square x x square, 4a square x square. plus now if I am differentiating this term, uh, there is no change for this term. It will just produce a minus 2a. So minus 2a, and this term is common. Both term will be having this e raised to minus ax square. So you can take it outside now. Well, you have e raised to minus ax square here already, and e raised to minus ax square right now coming again. So it will become e raised to minus 2ax square. E raised to minus 2ax square, and integration is there, minus infinity to infinity, a square is there, and dx. Okay. So again, it's a summation term. You can just make the integration into two parts and integrate it separately, and both are kind of non-form only. So first integration will be coming like a square 4a square. Anything else? No. Minus infinity to infinity e raised to minus ax square, x square dx, plus another term which is minus 2a square integral minus infinity to infinity uh, e raised to minus a 2a x square 2a x square dx. Okay, so this is one another form of integration, or this is going to be the more general expression than this. It's a standard integral again, minus infinity to infinity x raised to 2n e raised to minus ax square dx is going to be something like root pi by a. Now, depending upon the power of n, depending upon the power of x. Okay, one thing that you have to make sure is that you are having a even number as a power of x. Whenever it is odd, you don't have any value here, that is going to be 0. So even power of x will only produce this kind of an expression. So this will be like 1, 3, 5, etc. 2n minus 1 divided by 2 times a, 2 times whatever is the power n. So that is a general expression for any integration of this form. Okay, here in this expression, what we have is n equal to 1, and you just have 1 over here and 1 over here. So 2 times a, along with root pi by a, you have a 1 by 2 times a. Okay, so let us do that. Okay, one thing I miss here is this term is having again minus 2a square, right? 2 times it is coming. Here I have written, here I didn't write. This is minus 2a x square. Okay, so what we will have is a square 4a square, and this integration result is going to be root pi by a. A corresponds here nothing but 2a, right? Instead of a, what we have is 2a, and 1 by 2 times a. 2 times a is again 2a, so 1 by 4a. That is going to be the integration value of this particular. This is not there. Okay. Plus another term minus 2a square is there. Along with that, it's not plus. I think I myself will be confusing after some time. Minus 2a square integral minus infinity to, this is nothing but root pi by a, root pi by 2a, it will become root pi by 2a. Okay, so that's complete terms. This is like you have 4a square here and a 4a here. 4 and 4 can cancel. A square and a will cancel with each other. And what else? Again, I have a root a here and a over there. Okay, let me write it like that. Uh, Here again, I have 2a root 2a. So this will become root 2a. Okay, I'll take the a square commonly outside, and remaining terms are like, here I have root pi, and a square is came out already, root 2a, 2 pi a, that is the second term. And here what I will be having is root pi is there, and a root pi root a, if you cancel this, and divided by 2. Okay, so this can be solved like uh, a square, um, this is like, if you take root pi a outside, root pi a outside, 1 by root 2 minus root 2, so it's just like 1 minus 2 divided by root 2, that will give you 1 minus 1 by root 2. So this is going to be a square minus a square root pi a divided by 2. Okay, so that's a quantity psi naught dou square by dou x square psi naught. Along with that, you have another term in the first common cell, Hamiltonian cell, which is minus h cross square by 2m um, into this quantity, right? That is psi naught h psi naught. This multiplied with this. That is the first term of the entire energy function equation. Okay, so I just multiply this quantity with this minus h cross square by 2m into minus a square root pi a divided by 2, minus and minus, let's cancel. And okay, a square again I already found out, that is something like root 2 2a by pi, something like that, a square, let's see, root 2a by pi. Okay, so I can cancel that, minus is gone already, and there is a root pi over here, root pi over here, 2a 2 root 2 here and root 2 here, root a and root a, it will become a, and uh, this is like h cross square a divided by 2m. Okay, nothing else. So that is the first part of our Hamiltonian, and we have one more part, and in that part you have a constant multiplied, a constant half m omega square, multiplied with psi naught h prime, sorry, h cap psi naught. So I'll first calculate this and later I'll multiply it. So first this quantity is integral minus infinity to infinity. A square is there, uh, e raised to minus a x square, e raised to minus a x square dx. No differential operator or anything, you just have to do the integration. You can sum, there is no problem of ordering here. You will be having a square minus infinity to infinity e raised to minus ax square x square dx. Okay, that is again from the previous formula we will get, oh, 2 is here, 2a. This is something like a square root pi by a corresponds to 2a into 1 by 2a, that is 4a, etc. Okay, so a square is nothing but root 2a by 5, and here I can have 5 by 2a, and that will cancel with the 1 by 4a. So this is cancelling each other, and in addition you have 1 by 4a. And now my half m omega square, this quantity will become half m omega square divided by 4a, or m omega square divided by 8a. Okay, that is the second part. Now our energy expression is going to be, or energy function E is going to be the summation of this term and second term, I know, m omega square divided by 8a, and the first term is going to be h cross square a by 2m, h cross square a by 2 2m, 2m, I think so, yeah. So this is your final energy expression. Okay, so what we want is this value to be minimum for being a ground state. uh, we want to minimize this quantity, so minimum over the parameter a. So once you obtain the, just minimize it, dou e by dou a, that will give you here h cross square by 2m plus here m omega square divided by 8. This is minus a square, right? So this has to be 0 for minima or maxima condition. That will give you h cross square by 2m equal to m omega square divided by 8a square. 8a square minus 1 by u. Is that correct? Okay. From that I'll get a as m omega square. I'll calculate a square first. A square as m omega square divided by h cross square else is omega square divided by h cross square, and 2m here, so this will be like 2m square omega square and one 8 also coming here. So the 8 and 2 cancel. This will become m square omega square divided by 4 h cross square. That is a square. So a will become m omega by 2 h cross. Okay, so we got A as our minimum energy. A corresponds to the what uh, minimum energy, or you can just substitute uh, in your energy function E, which is something like h cross square A. So here you can substitute. You know, corresponding to A being uh, the particular value that we have, that corresponds to an energy of minimum, and you can substitute that value, and the energy corresponding to that will give you the minimum energy. So that is like h cross square by 2m into that number, h cross square by 2m into m omega divided by 2h cross plus what else, um, m omega by 8, m omega square by 8, m omega square divided by 8 a m omega 2h cross. Okay, so you can cancel a lot of things here. M cancelled, h cross square, h cross cancelled, and 2 and 2 become 4. So this will become h cross omega divided by 4. H cross omega divided by 4. Plus, here m omega is there, m is there, omega 8 will become 4 with this cancellation. So what else is there? Omega h cross divided by 4. That's it, right? Okay. So h cross omega 1 by 4, 1 by 4. So that is going to be h cross omega uh, divided by 2. Okay. So this is, according to this theory, variation principle, this is going to be the ground state energy of yours. So you know the exact solution of linear harmonic oscillator ground state energy. You know that expression E is equal to n plus half h cross omega. And what was the ground state energy? That is nothing but half h cross omega. So that means the variation principle here brought us the exact solution uh, for this ground state energy.